Well, we're going to get rolling. We're going to watch TV. Ironically enough, it's kind of about automation. So stay tuned. It's a guy by the name of Doug Weber, and he works for DARPA. Used to work for DARPA. Now he is off at university running programs and projects. And what you see here, I need to make sure that I've clicked the boxes here. What you see here is a screen title. It says BIOELECTRONICS, implantable, injectable, and wearable devices for sensing and affecting, that means manipulating, neurological functions. That's your brain and your nervous system. Down here, you see the Lang conference. You can look this up on YouTube, and there's all kinds of very, very smart people that talked at this conference. And then you have rice.edu. That's where I believe Dr. Weber works. Dr. Weber is involved in DARPA's N3 program as a lead participant that basically has contacts throughout DARPA for this neural interface project, non-invasive, non-surgical neurotechnology from DARPA. So this is just a taste. It's one flavor of a palette of flavors as it relates to jacking your brain and your nervous system into the internet. So without further ado, we will watch this in pieces.
We're going to go ahead for the next speaker, and that is Professor Douglas Weber. Doug is an associate professor in bioengineering department at the University of Pittsburgh, one of the leaders in bioelectronics. He was also a program manager at DARPA and led a lot of the kinds of projects that you've seen over the last several years. So his talk today is going to be on implantable, injectable, and wearable devices for sensing and affecting neurological functions. Please give him a warm welcome.
All right. Well, first, thank you, Raphael and Paul, for the invitation to come visit Rice University. I've been to Houston just a handful of times, but this is my first time spending any significant time on the campus. So I've been a fan of a lot of the work that's been going on here for the past several years. The growth of your neural engineering group is really remarkable. So congratulations on all your past and what will surely be future successes. So my work, even though devices in the title is in the title, my work really focuses on the neurophysiology of neural interface devices. And more, these devices are being developed and approved for use in humans. And the proliferation of both of implantable, injectable, and wearable devices is, I think, really going to change what's possible, not only in bioelectronic medicines, but in many other areas of medicine where interfacing with the nervous system can support unique and powerful functions. So I just need to start with a few disclosures. I do some consulting work on the side, and I get paid for that. So my lab is what used to be just a single investigator lab 13 years ago is now really a vibrant cluster of labs led by independent investigators that each have their own area of expertise, but by working collaboratively allows us to address problems at scale, and that is we can focus on the many aspects of a problem that, that limit our ability to implement new solutions, and by working together, tackle it. And I think, as you'll hopefully be convinced through some of the things we're doing in human neural prosthetics, is I think really a model of the way this work needs to be done, because these are complicated technologies, complex disease cases, and a single investigator is rarely going to be equipped to tackle all aspects of the problem. So we focus on not so much designing technology, but implementing technology that allows us to both understand as well as restore sensory and motor functions after injury or and also after disease. And so it's basically sensory motor function that we specialize in studying, and we develop neuroprosthetic devices to interface with different areas in the nervous system to both sense and affect neurological function. And I'll, through the course of my talk, highlight the various devices that we're using for these purposes. This is the group, so there's now nine faculty in total, spread across several schools at the University of Pittsburgh. Several of our faculty are actually clinicians, so I've highlighted in red those members of our group that actually see patients. That is
I'm going to pause here, and I want to point your attention to this little logo over here with the flag and the eagle. That's the Department of Veterans Affairs. So, just, there's a lot going on. When you hear about the president dealing with the VA, when I think about that with the research that I do, and I think about this idea of experimentation in an effort to provide therapy or a better quality of life, but in reality, perhaps maybe trying to learn or achieve some other objectives. There's a lot going on here, because we are talking about the nervous system and the brain, which drives basically all human activity.
The real doctors on the team that understand what it's like treating patients on the front lines of medicine, and thus their perspective in shaping the development of new technologies and interventions is really critical. And so many of our faculty have appointments not only at the University of Pittsburgh, but in the medical center affiliated with the university, as well as the Department of Veterans Affairs. We are fortunate to have many active collaborations, not only with other academic groups. I don't see Rice on this list yet, but I'm hoping to add that one before I leave and go back.
I want to point your attention to these companies here. And you've got National Institute of Health, FDA, DARPA, the VA, National Science Foundation. You've got BlackRock, which is a name that's come up quite a bit. And you have all these universities that are well-known and renowned. So off we go.
Back to Pittsburgh, but we work very collaboratively with many other academic groups. As well, we work with many small businesses to develop technology that can be commercialized for eventual human use. I'm a strong proponent of translational research, and I don't believe that you can call yourself a translational researcher if you're not actually working with companies that have devices that are on a road to commercial access. And of course, we're fortunate to be well supported by the various federal funding agencies and private foundations. Okay, so our work focuses primarily on developing science and technology for reducing the burden of physical disability. And I'm showing some statistics here for just a few neurological conditions that result in profound physical disabilities. Stroke, spinal cord injury, and amputation together account for 1 million new cases of these conditions every year. And for people that have dealt with any of these conditions and know what the current sort of best practices are in this field, you'll appreciate that there's a lot of room for improvement. The technology and the methods that are used to restore function after amputation have certainly gotten better over the years, but they fall far short of restoring what we would consider natural human function. And so our work and my belief is that the only way to really get to the level of function that we consider natural or normal is to connect devices directly with the nervous system. Our sensory and motor systems are responsible for so many aspects of our existence and our interactions with the world that it's only through connections with the nervous system that I think we can provide the level of function that we need. So what do I do for a living? I tap into the nervous system. So I used to work for the DoD, didn't do any intelligence work, so this isn't wiretapping in that sort of sense. But we are trying to tap into the underlying signaling that is going on in our nervous system when we think, act, and move around our worlds. And so for the people in the room that maybe don't stick wires in the brain, what I'm showing you here are some of the technologies that we use for these purposes. So shown at the center here is an enlarged view of brain tissue showing neurons illuminated with a green fluorescent protein. Shown at the right is a microelectrode array. This is a bundle of small wires that provide several windows into brain function. And by measuring the electrical signals that are generated by these neurons, which comprise our brain, we can examine the pattern of signaling that is occurring in support of many neurological functions. Okay, so if you've never seen the sort of inside of a brain before, and if you've never seen the language of the brain, that's what I'm showing here, is the electrical signals that are generated every time a neuron senses, processes, and transmits information. There's a pattern of spiking activity that is something we can detect with devices like this. Okay, so much of my work focuses on understanding what all of these little squiggles mean, how groups of cells work collectively in networks to support function through signaling cascades like this. Okay, and why does this matter? Because as I'll show you in the next few slides, we're trying to build devices that use signaling like this to communicate directly with the nervous system. Okay, so we want to enable the brain to have direct control over devices in its environment using capture of signals like this. And as well, we want to be able to go back the other way and restore vision, touch, and proprioception through stimulation of these sensory pathways as well.
Okay, so he's talking about using the brain to control devices, which requires computer involvement. And he's talking about being able to write information into the brain to do things like recreate sensation and things like emotion, and decoding these squiggly lines that is the analog output of the electromagnetic activity in your brain. And this has been going on for a very, very long time.
And again, it's knowing the language of the brain that is going to be key to making that possible. These are some examples of the types of devices that we use. I would say the majority of the work that is happening in the neuroprosthetics space is using implantable devices like this. This is the so-called Utah electrode array. This is a bundle of up to 100 small needle electrodes that can be implanted in various parts of the cerebral cortex to either sense or stimulate neural activity there. And so shown here is a picture of a human brain with a pair of arrays implanted in sensory cortex. Okay, so by making these electrical connections, we can study population activity in neurons of the brain on a fairly large scale. But those devices require surgery, so we have to open and expose the brain, which requires making a hole in the skull, opening the dura, which is the skin that overlies the surface of the brain. So it's, you know, I think Dr. Yosher would say that this is a fairly routine procedure, but for someone coming off the street, they might view this as somewhat invasive. And so less invasive approaches, such as with injectable devices, are also being developed. And so shown here at the top is what's called a Bion muscle stimulator, which was developed now a few decades ago by the Al Mann Foundation. This is a device that can be injected into muscles and nerves of the body and used to provide therapeutic stimulation. I've done work with the Bion in the past, but I'll talk about our work we're doing today with injectable spinal cord stimulators. So now we can place devices like this in the body, target deep neural structures without having to do invasive surgery. Okay, so injectable devices becoming increasingly capable and I think more accessible than most implantable devices.
So Utah Ray, this picture was 2015. These injectables, right? 2015, little RFIDs, grain of rice kind of thing, that are able to deliver stimuli to nerves. And they're talking about doing this stuff in the spine. And the important takeaway here is that when you think of an RFID that you're seeing rolled out on 60 Minutes or CBS or whatever, right, where they're talking about having a chip in your hand so that you can open doors and access things and pay for things, and this is the new thing to do, and in Sweden or whatever, everyone's got it, and this, that, and the other, making it glorious, this whole chipping thing. They make it sound like it's this passive technology that, you know, it's no big deal. It's just this passive thing. You have to be nearby something for it to work. And what this guy's talking about is they've got form factors, and this is credited in 2015 at the medical and institutional level, which means this stuff has been around a lot longer than that, whereby these things can read and write information into and out of your nervous system if placed in the right spots, in the same general form factor as what we're seeing rolled out on television, like a grain of rice, an RFID tag in your hand. 2015. This is part of the MK Ultra stuff that they don't really talk about, that wasn't really brought up in the public church committee hearings, this idea of cyborging people. Church committee hearings, MK Ultra, you think drugs and shock therapy. Well, there's this whole notion of radiotherapy, which we're going to get into. Bioradio, the electromagnetic responses of cells and human manipulation, if you will, various changes in the body and the physiology with electromagnetics, amongst other things. This is where we're going. With the implantable stuff, though, is this miniaturized version. These things you're seeing here, miniaturized, ultimately put into the body so they can't be removed. And then beyond that is this stuff is going to be grown using your own cells through genetic manipulation. And we'll go through those sciences as time permits.
But the ultimate would be something that doesn't require any surgery at all. It would be something that would be as simple as getting up in the morning, throwing on your shirt, and you would have the neurotechnology assistance that you need to support yourself. And so I'll talk about the work that we're doing with a company called Battelle to develop such wearable neural prosthetics. Okay, so just to provide the scientific background, you know, since most of our work really does focus on understanding the language of the nervous system, I like to show videos like this, which really shows kind of the underlying scientific foundation for much of the work that we do. So I'm just going to set this up. This is a picture or a video of a rhesus monkey. He's trained to perform a task in virtual reality. So the monkey's sitting in this chair. He's seeing a screen that is displaying an ellipse, and his job is to trace that ellipse with his left hand. While he's doing that, we're tracking his arm motion with cameras that are pointed at his arm and these reflective markers. And we're measuring through electrodes like this the electrical spiking that is occurring in the neurons of his motor cortex while he draws that ellipse. Okay, and what we're interested in is understanding the relationship between that spiking activity and the movement that's being generated. Okay, so let me play the video. So the popping that you hear, that's an action potential. That's the signal that is generated by an individual neuron, and it's the rate of those action potentials that is the code for the neuron. So what you may have noticed is that there's a very consistent relationship between the motion of the arm and the bursting activity in the neuron. This is a neuron that it tends to prefer or indicate movements that are up and to the left, and so it's groups of neurons like this that form the motor program or the neural code for planning and constructing movements. And so if you can assemble the activity of many such neurons, many such directionally sensitive neurons, we can then decode what it is the motor cortex is trying to do. And if we can do that in real time, then we can use it to control assistive devices.
So this guy just talked about being able to map the neurons specifically enough in real time to understand how to translate motor control into a device. Conversely, what they're going to show you with this sleeve is being able to input those same sequences, that sophisticated, real-time, specific firing of specific neurons in the nervous system to actually create movement, artificially stimulate movement in a human. So just let that sink in, that external devices, external energy, if timed and modulated properly, if targeted properly at the right neurons with the right stimulation and the right sequence, can artificially stimulate your movement like Pinocchio, like a puppet, like an automaton, kind of like what we just read, this automation of the world through this homogenized New World Order idea, this premise whereby everything is controlled from the top down through automation, which when you look at the fourth industrial revolution, which is what we're going through right now, this great reset is ushering in the acceleration and the permanent foundation, if you will, of this fourth industrial revolution that is the underpinnings of our future, according to globalist ideology, whereby automation is the central driving force that implements government. Automation implements government. And down to the level that we're looking at today, right now, here, is this idea of decoding the human, whereby you can automate the human. And it's being presented as a medical endeavor to help those that are not able to move themselves or think or process information on their own. Once this stuff is developed, it's here. And how is it going to be used is the real question. Because if you can override a nervous system, if you can artificially apply stimuli to the nervous system to create movements that are controlled and intentional, does it stop at the motor cortex? Are they able to do it with thoughts? Are they able to do it with emotions? Can they do it with visual imagery? Can they do it with audio? Can they do it with smell? The answer is yes. And then the next question we need to ask ourselves is, what does this look like? What is watching of entertainment? What is experiencing entertainment look like in 10 years, in 20 years? Are you even going to want real people around you? You might, but what about the children who are 10 today, or the children who are just born today? Will they? Think about the love and dependency of technology that people under 30 have today relative to those that are 40 or 50 or 60. And look at the trend, look at the trajectory, and consider what we're talking about here. And how this stuff can be packaged in a nice, neat, clean, sexy, seductive way so that people will want this integration in order to simply survive and to be entertained, while the physical space is being constricted and we are put on lockdown and put onto universal basic assistance and to be phased out, basically. I mean, that's really what that letter was talking about, from the Archbishop to the President of the United States. Anyway, let's continue.
With that, I'm going to show you a video now of Jan Sherman. So Jan was the first volunteer in Pittsburgh to have these microelectrode arrays implanted in her primary motor cortex. She has a condition called spinocerebellar degeneration, which has left her paralyzed from the neck down, so she can't move her arms or her legs. Her respiratory function is mostly preserved, and interestingly, her somatosensory function is preserved as well. But in any case, she's completely paralyzed. And so she read about our study online and wanted to be, and literally called us up and said, I want to be the first person in Pittsburgh to do this. So Jan came in. Jen Collinger is leading this project. Jan was implanted with a pair of these 10 by 10 microelectrode arrays in her motor cortex. She had connectors emerging from her scalp for the 3+ years that the electrodes were implanted. She affectionately referred to those as Lewis and Clark because she certainly views herself as an explorer. But over that 3-year period, we were able to study Jan's ability to control a variety of assistive devices using just her brain signals. So now I'll play the video.
Months after the surgery, we came back to see whether she would be able to control the robotic arm with nothing but her thoughts.
So there's
they
Lewis
plugged
and
her
Clark.
brain into the computer, and this is what we saw.
I can move it up and straight down, and left and right and diagonally. I can close it and open it, and I can go forward and back.
That is just the most astounding thing I've ever seen. Can we shake hands?
Sure.
No, really.
Yeah.
Like, come right over here?
Yes, you come over there.
Okay.
You grasp your hand there. There we go.
Oh, my goodness. Wow.
And I can do a fist bump if you'd like.
That's amazing.
I think it is really amazing, and you know, I can't emphasize the importance of the underlying neurophysiology, right? It's understanding that neural code that links activity in a group of neurons to some action that the person is performing, or in Jan's case, trying to perform but can't because of her injury. And
so you just saw that. She's talking, completely calm, carrying on as if that arm moving was her own arm. And it really speaks to the power of the brain, being able to learn and adapt and to I guess, reestablish a sense of normalcy, if you will, at whatever that is, however you want to define that. For her, it was through the use of this arm that's fixed to something that she's able to remotely control if she's literally plugged into it. But again, what does this look like when these signals are put into the brain? Not reading it out so that it can be, not only reading it out so that it can be used to power a prosthetic. What happens when these are put into the brain? What are the applications of this for the military? Could you correct subtle mistakes made by soldiers in order to ensure mission success by stimulating their nervous systems? Could you get a group of soldiers to function as a drone swarm, but still having some autonomy? What does a cybernetically enhanced military look like? Why are these people doing this stuff? And if it works for that, don't you think that giant corporations would also like a hive mind for their little employees, their human resources, their human capital? What would school look like for children? What is it that we're seeing in schools today with this mandate for similar thinking, what to think, not how to think. And this is a mechanized way to ensure that the conditioning and the behaviors result in an expected and intended, and most importantly, a type of automated outcome.
And so it's understanding and being able to model that relationship is what allows people like Jan to control devices like this. The other thing that I think is really amazing is just how arbitrary and free-form her movements are. Right? And she's not like intently focused on the arm. She's having this conversation, she's cracking jokes, she's making very impromptu decisions about what she's going to do and what she's going to tell, in this case, Scott Pelley, and it's all very effortless for her. Right? And that's because she's learned how to modulate the activity of just a few hundred neurons in her motor cortex very effectively. Okay, so that's what we're doing, some of the work we're doing with brain implants. We're also developing interfaces for the peripheral nervous system, including the spinal cord, which is not technically part of the periphery, but by interfacing with spinal cord and peripheral nerves, I think there are many other types of functions that we can support, and again, perhaps through slightly less invasive means. So now I'm going to shift gears a little bit and put my DARPA hat back on. Paul is here, so don't report me to the DARPA police. I spent 4 years at DARPA from 2013 to 2017, and I started a program called Haptics, which was aimed at creating peripheral implants to restore sensory and motor function for amputees. And one thing that was really important for us when we came up with this program is we wanted to have something that was going to be not only high performing in a laboratory environment, but would be robust and reliable enough to take home. Right? We've seen, over the past many years just how exciting and powerful these neural interface technologies can be, but until you can use them at your home, in your community, I think we're, are falling far short of our eventual goal. So I think a hallmark of the Haptics program is that these are technologies that will be suitable and robust enough for home use.
So let's study this for a minute. Natural control, touch, and proprioception, that's awareness of where your hand is in three-dimensional space, for example. And what you see here is an implant, right? Electrodes in the nerves, wirelessly transmitting motor signals to a prosthesis, wirelessly transmitting this data. Nerve cuffs, some type of stimulator / reader, and a wireless interface to your brain.
So the program involves a variety of implantable devices for measuring nerve and muscle activity that drives movement, and for stimulating sensory pathways in the residual limb to restore sensation. Okay, and so for amputees that have advanced prosthetic hands, the goal is to create a hand that looks, moves, and feels like a natural limb. Okay, so here I'm going to show some work from Greg Clark's lab at the University of Utah. They are working with a number of amputees, upper limb amputees, that have these Utah slant electrode arrays implanted in their peripheral nerves of their arm. So this is an array of 100 electrodes that span several depths of the nerve to record or stimulate activity there. And so I'll just show one of the videos from that. So now, this is a gentleman that actually has, I think, a bilateral amputation. We're measuring, Greg is measuring neural signals from his residual arm, and he's decoding those signals to drive wrist and finger movements in this virtual prosthesis. And you can see that.
All right, so I'm gonna break this down. The guy has no elbow, nothing below the elbow. He just has like part of the top half of his arm, and they are taking the neural signals basically from his brain. They're tapping in probably to his peripheral nervous system, but they're taking the signals from his brain, and he's imagining moving his wrist and his fingers, and they're actually getting feedback on that and showing him what he's trying to do on a screen. So what you're seeing on the screen is a decoding of his brain, even though he literally doesn't have a wrist and fingers anymore.
There's independent control of each of the 5 digits. The wrist has 3 full degrees of freedom that are able to be moved, very accurately, very smoothly. Again, through direct coupling of motor intention in the nerve to movements of the prosthesis. Okay, so that's showing another way to do motor control. Now I want to show you how we're using this technology to restore touch sensation. So using that same peripheral nerve implant, but stimulating rather than sensing activity, this gentleman is going to demonstrate the first time he feels virtual contact through his sensory interface. So just to set this up, he is operating this virtual prosthesis in a virtual reality environment that simulates the contact forces that are generated in that virtual world. So there are virtual sensors on this hand which report when the hand comes in contact with the environment. If we take that virtual sensor data and we send it out to stimulators that are coupled to these electrodes, we can restore that sensation of touch. And you'll see what that feels like for this guy.
Oh my God, I just felt that roar. Oh yeah.
Can you feel the fingers sliding when you do that?
Yeah, actually I can. I can get it on there. God, that is so cool.
But it's so simple, right? It's one feeling of touch sensation. But this is a gentleman that hasn't had either hand. He had both of his hands removed after an unfortunate accident, like 13 years prior to being part of this study.
So artificial sensation applied to the brain to provide a sense of touch to the extent that textures are understood. Feeling the door, feeling the grain of the wood, so to speak. So once these are all decoded, what are the applications of this? Beyond being, injured or paralyzed. When you think of the entertainment industry, when you think of this idea of robotics potentially replacing workforces where you get paid to log into a robot, to have the robot perform work in a warehouse, and you get all of the sensations that a human needs to be able to efficiently pilot the robot. And another application of this would be something like sending a robot to an asteroid and then having the robot perform human-like tasks and not having to have life support systems, etc. There are good applications for this. But the bottom line is, when you look at commercializing these types of applications, particularly providing sensation, how was the internet built, folks? What really funded the internet? One of the major funders of the internet. And you can see where this idea of sensation may go from an entertainment perspective, quote unquote. But commercialization of this kind of technology goes far beyond just entertainment. There is some practical applications that are useful, I think, for building infrastructure, so to speak, or for generating some type of productivity, not just mindlessly wasting time. But once they're here, once these technologies are here, how are they going to be used? And are you going to have to put something on for this stuff to affect you? That's the next step to all of this when we start getting into electromagnetics. Are you going to even have to have anything on to potentially have access or be accessible to this idea of automation?
So I think this is the tactile equivalent to going blind. You know, imagine not being able to feel anything, a loved one's hand, that cold beer that you have at the end of the day. You know, you get so much sort of benefit from being able to explore your world, not just visually and auditorily, but through haptic feedback. And so for this gentleman, you know, having some of that brought back was a pretty big deal. Okay, looks like I better move. At my lab at the University of Pittsburgh, we're doing some similar work, but again, with an eye towards less invasive ways to implement technology like this. We're using spinal cord stimulation, which shown in this animation here. Spinal cord electrodes, such as the one shown here, can be injected through the skin, tunneled down to the spinal cord, targeted laterally where the peripheral nerves enter the spinal cord, and give us access to those primary inputs to the spinal cord. And because those nerves are conveniently laid out almost like the keys on a piano, by taking our electrodes and straddling those keys, providing a number of contacts across a bundle of those nerves, we can kind of provide the punctate sensory inputs to the spinal cord. Again, all in a device that is approved for human use and easy to test. Okay, so our goal is to be able to take touch sensor data from a prosthesis and play it back to the spinal cord as a pattern of electrical stimulation that is distributed across the keys of those nerve roots coming into the spinal cord.
So they're taking existing medically approved devices used for pain management on the spine, and they are running different data through it. It's not just data to numb or distract pain receptors or the sensation of pain in the brain. It is, in fact, to provide sensation in this case, or motion. So you're seeing prosthetics, you're hearing prosthetics, right? Well, imagine no prosthetics. Imagine you still have your limb. What happens if you just broke your back? Right? What happens if you just broke your back? I mean, you still have your legs, you still have your arms, you still have your hands and your feet and all that. And they can put this stuff in there and you get mobility again. Like you're not on crutches, you're not in a wheelchair, you're not, you know. And then beyond that, you see here on the right, you've got these electrodes. Can this stuff be applied in other ways? Does it require surgery? I mean, we are looking at implantable, injectable, and wearable devices. Injectable could be things like nanotech. Injectable could be things like genetic information to go in and reprogram your cells to grow and or express new methods or new ways or new interfaces for things like wireless energy, be it light, sound, or electromagnetics, where you get a hybridization, not a surgery where electrodes are implanted in there with a wireless receiver and a battery and all of that, major intensive surgery. No. Something that perhaps is a combination of synthetic and biologic nanotechnology, biotechnology, so that you get things like luminescent nanoparticles that stimulate light receptors in cells that fire your nervous system, activate your nervous system, or suppress your nervous system, or things like electromagnetic energy or infrared light, which passes through the skin and bone very well, or ultrasound interacting with whatever is deposited or grown on or around your nerves or in your brain. And So what we're talking about here is this progression of technology, this miniaturization and sophistication of technology. And if you don't think it's possible, I submit to you a plethora of examples. A car. You went from walking to a horse and carriage to a Model T to the cars we have today. Automated Teslas, for example. That's what they're telling us is the latest and greatest. That's what they're telling us is the latest and greatest. I mean, you could take human motility and look at aircraft, fighter planes, etc., and you could see how technology advances. Computer, what used to take up in like a huge room at a college campus is now we now have devices in our pockets that are infinitely more powerful, exponentially more powerful than that. So it's this idea of refinement and miniaturization that will ultimately lead to what I'm referring to here, where things could be injected, inhaled, absorbed into the body, whereby then the body either grows or assembles and assimilates these types of electrodes, if you will, to interact with the nervous system. They're showing you things that they're out in the medical field. They've been out for a very long time. We're way beyond this technologically, in my opinion.
And so shown here is some data from 3 different subjects. Much of the work that we're doing right now is really focused on mapping those inputs to the perceptual experiences that the subjects have. So each electrode is overlying a different bundle of nerves, driving sensory inputs that are referred to different parts of the body. And so as we map those keys out, we can see what parts of the body image we can reconstruct.
Yeah, so everything I just said, right? And here's this guy literally breaking down at a very high level this idea that these nerves are tied into specific parts of your body, and that when they have these arrays, either on your brain or in your spinal cord or on your peripheral nervous system, because your spinal cord is part of your central nervous system, you get access to different pieces of the body to either read what's going on with that piece of the body or to stimulate that piece of the body. So when you see prosthetic, hopefully what you also see is this idea of being able to override organic, whereby a perfectly functioning arm could potentially be automated, could be overridden using the very same techniques, the very same software, the very same databases, the very same algorithms that are used and developed for people who are paralyzed, people who have disabilities, people who have mental illness, et cetera, et cetera, et cetera. Because once the software is there, it is a matter of refinement, and then it is a matter of deployment. And that's where we get into platforms, architecture, infrastructure. What do the platforms, the architecture, and the infrastructure look like to deploy something like this to the masses? And who would have access to that? What companies exist today with the architecture and the platforms to be able to reach out and connect with anybody at any time? And then I ask you, do these companies, are they the same companies that house and manage AI, house and manage cloud-based data, house and manage the information for the world, be it other businesses, corporations, and or governments? And I submit to you groups like Google, Amazon, Microsoft, Facebook, Twitter, and all of your major telecommunication companies. They are nice and quiet right now, aren't they? All of your major telecoms. They're nice and quiet because they see what's happening. Their competition is about to be leveled, and they are going to be able to scoop in and buy up pieces of these platforms that I'm referring to. The telecoms will. They're already doing it. Things like the AT&T Time Warner merger, for example. Their acquisition of HBO and others. They are buying platforms. They are buying infrastructure. All of that stuff came with television broadcast towers and satellite links, in addition to cloud-based data center storage stuff that is right in their wheelhouse, AT&T's wheelhouse. So when you think big tech, it's not just big tech. It's also big telecom. The wireless piece, the internet piece, it's telecom. And they are going to be the ones that scoop up the fractured pieces that hopefully will be big tech in the near future. So they're the ones, in my view, that need to be watched as well. Primarily because they're the ones responsible for managing internet traffic. You know, the ones that are supposed to be looking out for things like pedophilia traversing the internet. At the link layer level, at the metadata level, not at the application level, not at the post where you look at the picture and the words on your Facebook feed or your Twitter feed or whatever. No, that's the application level. I'm talking at the metadata level, at the link layer level. They can reach in and look at data that has packets of information going to thousands, if not millions of different addresses all at the same time, pipes of data, city to city, country to country. They can reach in and look at that stuff, packet by packet by packet. That's the power of telecom. And nobody's saying boo about that. They're being nice and quiet right now. And they're the ones that are going to be running all of this automation stuff, the fourth industrial revolution stuff. They're going to be the ones managing that network traffic. You'll have the people on the end, the big tech on the end, doing your applications, and you're going to have telecom in the middle, running the data to and fro, being able to pick out whatever they want, look at whatever they want. AT&T has the contracts for the federal government. They are responsible for securing all their networks. They provide their email. They provide their encrypted everything. That's just one telecom. There are others out there that have the same types of sensitivity, so to speak. So I'm digressing. Your nervous system basically is able to, they can map out which nerve talks to which piece of your body, and they're talking about reading and writing information to and from each specific piece of your body and deciphering and decoding that, and then putting that in a database so that they can stimulate your brain and read your brain or your nervous system to drive prosthetics or to potentially automate a perfectly good arm or leg or hand or fingers.
Okay. And as well, one of the things we're interested in is not only where in the limb we can recreate these sensations, but what do those sensations feel like? And so shown in these word clouds are the various verbal descriptions that we've gotten from our subjects describing the sensory experience that is associated with that electrical stimulation. In most cases, there are things that we would associate with as sort of unnatural, electrical, or at least in some cases unpleasant, but as Daniel alluded to earlier in his talk, there's a large parameter space to explore here, and understanding what the right code is for creating pressure and touch sensations is an important part of this research. Okay, but the important thing is that by working with humans with FDA-approved technology, we can make progress much more faster than trying to do a series of animal studies where you can't really have a conversation about what they're experiencing, whereas humans can describe it in often vivid form. So the primary goal here is to restore touch sensation such that it improves the amputee's ability to operate their prosthesis. But a secondary, maybe primary benefit in the eyes of the amputee is that by restoring these sensory inputs, their experiences with phantom limb pain seem to be improved. That as many amputees experience what's called phantom limb pain, it's probably associated with the loss of sensory input from the limb. And by bringing that sensory input back, many of these amputees report that their pain goes down. So we think that in addition to the sensory motor functions that this technology provides, that there's an added benefit of pain reduction. Okay, so we're also exploring wearable devices. So we for a number of applications where, especially where permanent restoration of function is not required, if you're interested in therapeutic assistance, then having a device that you can use for a period of time and then eventually grow out of would be desirable. So I'm working with a company called Battelle. They're a research organization, not-for-profit research organization, just a few hours from Pittsburgh. They've developed a technology which we call the sleeve electrode array. This is a garment that has 160 electrodes embedded on its inner lining. When you close that garment up around the forearm, it blankets the entire surface of the forearm from wrist to elbow with 160 of these electrodes, which we can then use for either measuring muscle activity or stimulating muscle activity. And so if we stimulate muscle activity, because we have, again, sort of like the keys of the piano, because we have an array of inputs that we can work with, we can generate a variety of different hand movements by stimulating different electrodes. So,
all right, you wanna watch that again? Let's see. Do you see what that guy did? They've got a little box over there, and they're hitting certain switches. This is a laboratory environment where they're looking at very specific sequences of these little dots, these little electrodes being fired at the same time or in succession or any combination of ways, very specific recipes, so to speak, are lined up on these switches, and they're able to get this hand to do things all by itself by directly stimulating the nerve. So after saying that, let's back this up a touch and watch it again.
They've developed a technology which we call the sleeve electrode array. This is a garment that has 160 electrodes embedded on its inner lining. When you close that garment up around the forearm, it blankets the entire surface of the forearm from wrist to elbow with 160 of these electrodes, which we can then use for either measuring muscle activity or stimulating muscle activity. And so if we stimulate muscle activity, because we have, again, sort of like the keys of the piano, because we have an array of inputs that we can work with, we can generate a variety of different hand movements by stimulating different electrodes. So if there was wrist movement, we had different patterns of finger movement and so on. And again, because these are like the keys of a piano, we can construct arbitrary symphonies with input across that array. Okay, and so the goal is to create a fully wearable system such that there's a portable box that controls stimulation through the sleeve. It can be worn on a belt and then used in the home to support activities of daily living. So I'm just going to play a video here showing a volunteer at Battelle in Ohio State that has C5, C6 spinal cord injury, and so he has very limited hand function, but using stimulation delivered through this sleeve, he's able to grasp, in that case, a tennis ball. Okay, so this is using a portable array, portable and wearable technology for reanimating hand function. As I mentioned, though, we can also use this as a sensor array, right? So in addition to being able to stimulate muscles that are paralyzed, we can also measure the activity in muscles, which you might think, is there any electrical activity left in the muscle if the hand is truly paralyzed? And the answer is yes, and I'll show you how important that is in a few slides. But now we have a way to both sense what's going on in the arm. We can use that information for diagnostic purposes. We can identify unhealthy patterns of coordination in the hand after stroke and spinal cord injury. And then we can use electrical stimulation to treat deficits or to restore healthy coordination of muscle activity, all in a single garment. Okay, so I'm going to show a video now showing our ability to decode hand gestures from that pattern of muscle activity. So shown at the bottom left of this screen here is an avatar which is displaying a target gesture. And then the center avatar shows the decoded gesture from the muscle activity. So by looking at the pattern of muscle activity that is generated during these different movements, we can predict with very high accuracy what's going on in the hand. Okay, and so if we can do that in people with impaired hand function, this gives us a way to control assistive devices in a very non-invasive wearable form.
So they're training algorithms. They're creating algorithms, however you want to look at it, where you had something demonstrate what needed to be done, and then the sleeve measuring the actual function of it being done and that being recorded. And that one of those actions would be a single sample. And you would sample and sample and sample and sample and sample and sample until you have a large amount of data for a particular movement. You'd average that out, and then you can then start applying that to a stimulation protocol for paralysis. And the more samples you have from the more people that you have, the more effective and efficient and useful that algorithm is going to be. We're going to leave it with wearable right now. And just imagine what it could be if they could already sample a nervous system without any contact. Or if they could sample the nervous system with something as sophisticated as a smartwatch or headphones, or having a mobile device near your body, in your pocket, on your waist, in your bra, whatever, in your hand. Can they do it with radar fields? Can they sense your nerves or your muscles as they move to and fro and send signals to and fro with radar fields? And I'm asking you these questions, open-ended questions. I have my own opinions, my own experiences, so to speak.
Okay, so here is just some very early work showing what we're doing in stroke. So here we have a person with very weak hand function. His ability to extend his wrist and open his hand is highly impaired because of his stroke. But if we look at the underlying patterns of muscle activity that are generated in the impaired forearm, we see that even though he's attempting but able to perform only weak movements, there's very strong, easily detectable activity that we can use to predict the different classes of movement that we're asking him to perform. Okay, so this is a very impaired hand that still reflects, I think, a very strong will to move. Okay, so that's after stroke with some preserved hand function. This is work that we've done at the University of Pittsburgh with one of our BCI participants who has absolutely no hand function. Okay, so because of his cervical spinal cord injury, he can't move any of the digits of his fingers. Yet when we ask him to try moving those digits, we're able to detect very strong bursts of muscle activity in his forearm. Okay, so that means that there's spared connections between his brain and his muscle. There aren't enough to generate functional movement, but there are enough to be able to be detectable using our sensor array like this. And if we look across a range of individual finger movements, we can decode with very high accuracy which movement Nathan is trying to express. Okay, so that means that there's sufficient information in that impaired forearm to drive assistive devices. Okay, and it looks like I'm out of time, so I'm just going to wrap up by saying briefly that more and more we're trying to shift this technology from in-lab use to home use, and creating wearable and particularly portable systems, not just individual devices, but whole systems is going to be essential for that. And I hope I've convinced you that by coupling technology directly to the nervous system, there's a wide variety of, I think, very useful functions that we can support. And more, these advanced capabilities are becoming accessible for human use because of advances in injectable and wearable devices. And so with that, I'll take any questions.
Excellent. Thank you, Doug. So if you have any questions, line up at the mic. We also have some good questions online, so if you still want to put in some questions online, go ahead and do that. You have a question? Go ahead.
What controls the dexterity of the prosthetic? Is it the spatial resolution of the electrodes?
For the BCI work?
Correct.
Is that what you're talking about?
Yes.
So that is a function of the decoding setup that is implemented. So that arm that you showed, that I showed in the first video, that has 22 degrees of freedom, but we don't use all 22 degrees of freedom in all cases. So we start with a simple task, 2D movements in a plane, then we move to 3D, eventually 7D, so you have reach, orientation, and grasp. And they've gone as high as 10D, I think.
Perfect. Thank you.
Yeah, sure.
So start basic, and then more and more complex. This guy said he went as far as 10D. So out, in, up, down, left, right, rotations, sensations, all with time associated and pressure. Decoding what each of those subcomponents are from the brain or to the brain to drive, in the case of the question, a prosthetic with a certain amount of sophistication and selectivity. It's really remarkable when you think about the amount of data, the amount of information that needs to be read and understood and then processed and then potentially transmitted back into the body.
I thought it was very interesting to see that even in spinal cord injury cases that there were still connections going to the muscles. I'm curious, is that something that's generally clinically assessed? Is there a widespread appreciation of whether those signals are there for a lot of people, or was this an exception?
So other groups have used muscle activity below the level of the lesion for control like this. Generally not to this level of dexterity, though. I mean, we're decoding individual finger movements. Usually it's just hand open, close. But I think more and more the field is appreciating that just how much spared function there is, even in people that are diagnosed with complete spinal cord injury. There's been a lot of work in the last year showing publications of recovery of voluntary function after spinal cord stimulation in people with paraplegia and clinically complete, motor complete spinal cord injury. Right, so if there is any recovery of voluntary function, that means that even though the clinical diagnosis is complete injury, that means that there's some spared pathways that are again, too weak to show function, but maybe suitable to support a neuroprosthesis.
Would you have a recommendation to neurologists or rehab specialists, could there be this population of people who could be immediately helped?
Well, so I think what we need are better tools for diagnosing or predicting who might be candidates for some of these advanced technologies. And I think one of our goals for this sleeve array technology is to obtain a better estimate of the extent of spared connections that are there. So we just started a project with a group that has expertise in motor unit number estimation, so they can count like individual motor units in an electromyogram. And so if we can actually put a number on the number of spared motor neurons that are there, then that might be useful for predicting, this is a person that is a candidate for occupational therapy and recovery of some natural function versus, this is someone that's going to require an assistive device.
Yeah, that's really cool. Thank you.
Sure.
Let's take another one over here.
Hi, for the implantable devices, how important is it to target the specific neurons that before the damage would have controlled that effector versus could somebody just be retraining themselves to use a different neural population to control
that's a really, really interesting question. My personal belief is that you should try to get as close to that original structure as possible. You can teach an old dog new tricks, you can learn new skills, but it's just harder, right? And so the closer you get to the, to the original area responsible for that function, I think the better you'll be. So, it's something we're looking at on the sensory side as well, because we would like to be able to remap sensory areas, because it's actually a little bit more difficult to map out the sensory parts of the nervous system before placing these electrodes. And so if we could shift receptive fields or projected fields post hoc, that would be very beneficial.
Okay, one more.
As opposed to patients or subjects who have undergone amputations or paralysis who have used limbs before, have you ever tested these technologies on people who are born with inabilities, or disabilities, or who had disabilities such at young age that they never used arms or legs before?
So I'm not aware of any studies in the somatosensory system that have looked at that. For sure there are people with congenital defects, and missing limbs, that are born that way, and they are able to learn how to use myoelectric prostheses. There hasn't been any work, as far as I'm aware of, on the somatosensory side, but in the auditory field, cochlear implants, are given to children that are born deaf, and they're able to develop functional hearing, speech perception, using, with training with the cochlear implant. So I think the brain has the capacity to, to take on those skills, even if it, maybe didn't start that way.
Great. Okay, so we have one Slido question. So how long does it take to train a patient to control a prosthetic device?
So at that point in the study that we showed there, Jan was approximately a year into the study, but literally on the first day of testing in the lab, she was able to do 2D movements, and she probably could have done 3D movements. We just didn't do 3D testing that day. So I mean, it's super fast, because we try to approximate as closely as possible the natural coding scheme for the neurons. Right. Okay, and the way we sort of unmask that in someone that's paralyzed is we show them videos of the movement that we want them to generate, and through what some call the mirror neuron system, it generates observation-related activity. So as you're watching me wave my hands, your motor cortex is lighting up and encoding hand movements. Okay, so we can evoke through a visual display the natural coding scheme that we want Jan to use, Jan and the others to use in driving the prosthesis. And that.
So that's kind of a big deal when you think about looking or watching or observing something. 70% of our information intake is through sight, through vision. And what this guy's saying, Dr. Weber's saying, DARPA head guy, what he's saying is that when you see somebody doing something, your brain is encoding what you see. sounds like a very basic, obvious kind of statement, right? What does that really mean? And what the example he said was, if I'm waving my arms around and you're seeing me do that, and your brain is encoding those arm movements. And so what he's getting at here is that they can tune or train or zero or calibrate someone's brain simply by that individual looking at stimuli. And what are we all doing right now? What are all of our children doing right now? And again, I submit to you, do we really need contact on a whole sleeve or something that's been inserted after undergoing anesthesia and being cut open with a scalpel, or something that requires a bone saw? Do we really need all that today? And as we go forward over the next few episodes, I'm going to show you the answer is no, we don't.
That works very well, and so
so it's very intuitive.
It's very, very intuitive, and then that's really important for the learning aspect of it, right? Mm-hmm. If you're going to ask somebody to learn a complex skill, then their ability to translate feedback into change in function is really key.
Right. Excellent.
Caleb.
So the video that you showed when you were talking about somatosensation was very interesting because the student asked the patient to slide. Slide or texture seems like it's one of the most complicated features to stimulate because it involves both spatial and temporal.
No doubt.
So it's related also to the end stuff. To what extent do you think that it's critical to be able to control, to do sort of simultaneous activation versus sort of temporal pattern? Like, are they both critical, or is one more?
Can you repeat that and just
sure. So the question is, what are the essential, correct me if I'm wrong, but I think your question is, what are the essential features of the sensory code for something like touch or texture sensation?
But presumably the same question applies also in the effector space.
Sure. Well, I think we know a lot more in the effector space, but your question was on the sensory side. You know, the reality is we're still at such an early stage, and we're at least 10 years behind the motor folks, right? Because the motor work has been ongoing since the early 2000s in humans, and it's really just in the last 5 or so years that we're doing work like this in humans on an appreciable scale. So, you know, so we're still very much working at a single or small channel count scale. So addressing questions related to the spatial patterning of activity, I think we're not ready to do. On the temporal side, one of the challenges is, you know, so the sensory nervous system and probably many neurons in the nervous system work this way, but undergo habituation or adaptation. You know, so when you put your shirt on in the morning, you feel it for a period of time, but then eventually you ignore it because your brain adapts and it filters out what information which it presumes to be unimportant. And so if you bombard the nervous system with electrical stimulation like this, the sensation will be strong initially, but then attenuate gradually. And so figuring out how to work with that adaptive encoding scheme in the nervous system is one of the many challenges that we're facing.
Okay.
So this guy just said that they've been working with the motor functions for the last 10 years, and that's what he's going to disclose to you. So this was in 2018. So back in 2008 is when they really started going hot and heavy with decoding literally motor functions, moving an arm or a leg or rotating or grasping or whatever, right? And then he was getting into this idea of sensation or touch, and that's just a more recent approach. And that probably did come post the Brain Initiative put forth in 2013 by the Obama administration to decode the brain to understand very specifically what's going on with it. So you've got basic prosthetic movement, automation of a limb that's been removed or damaged or never had one. to now this idea of sensation, touch, hot versus cold, you know, gentle versus abrasive or harsh, sensation. And what is sensation? When you think about sensation, much of how we experience the world is done through sensation, through touch, and the different types of touch, different types of contact would be a better way or a different way to say it.
Yeah. All right. Thank you again, Doug.
All right. So
our next speaker.
We're not gonna listen to the next speaker. That looks really, really interesting, though. This says creating electronically controlled microorganisms with synthetic biology. It's a 35-minute discussion. I'm gonna sneak peek this real quick and let's see. I'm gonna watch this, and then we may watch this together because this gets into electronically controlled microorganisms with synthetic biology. We will likely get involved with this perhaps on Sunday, Monday, because this looks really, really interesting. And this is going to be way super scientific. So I want to watch it first, because if it's like too much medical jargon and stuff, it may be too much. But what this really, I think, is going to speak to is this idea of using energy to manipulate microorganisms. And it's just, wow, super interesting. So we have 15 minutes left. You can find this on humaninternet.org, this bioelectronic speech, and there's others that we may get into. Transient bioelectronics. There's the neural dust. We may watch pieces of this neural dust platform. And we've watched some of these already. We may watch them again. And here's the organic materials and devices for interfacing with the brain. That looks interesting. What I want to take you to here, though, is this idea of brain Q. And the reason why is we listened to Doug Weber talk about being able to rehabilitate people, where they stimulate the nervous system after an injury or whatever, and they get some function out of it, right? Some better function out of it. So I want to show you this. This is a company. Google is funding this company, and IBM likes this company. Google and IBM. Google and IBM.
Ago, my grandfather had a stroke. All of a sudden, half of his body was paralyzed. He could no longer grab this bottle of water, which I brought with me, especially here. He could no longer go to a shower. This was his state, and it remained for the rest of his life. Every single year, hundreds of millions of people suffer from neuro disorders. Motor disabilities following neuro disorders are an imminent need. To give you one number, stroke alone is forecasted to cost the US healthcare economy $240 billion by 2030. But the current solution is quite limited. It's called physical therapy. Many of you know it. It's a tedious, repetitive exercise of the hand or the leg in order to retrieve some of the functionality back. But it's just not good enough. and it's been there for a while. And BrainQ is here to change this equation using data-driven tools. Our mission in BrainQ is to lift paralyzed people out of their wheelchair. And when I say lift them out of the wheelchair, I mean literally being able to walk again or grab this glass of water again. And we do so based on two pillars. One is several decades of brain-computer interface research, and the other is rapid developments in AI tools in the recent years. When coming to approach this unsolvable problem, call it this way, on the whiteboard, we said, why don't we model physical therapy using data tools and apply them directly to patients' brain? Well, what do I mean by model physical therapy? Let's think about the brain as a sophisticated radio, where there are many different radio stations that work in parallel. And you know, I'm holding this in my hand and I'm thinking about my wife at the very same time. And these are maybe different radio stations. And our goal is to find the right stations which are associated with specific motor functionalities which are now lost. But the problem is that in order to do so, you need to interpret relevant data. And the relevant data, which is called EEG, the brainwaves, is a very noisy data. And you need a lot of good quality data in order to work with it. And this was a non-existent, essentially. So we had to create our own. We are the owners of one of the world's largest BCI motor task databases in the world, which we have created ourselves. And with this data, we've actually created state-of-art machine learning algorithms that can tell what are the radio stations for healthy people when they're grabbing this bottle of water.
Okay, so these people, you can see down here, Google, you have some university here, can't really make out that logo. IBM, you have McGill, and some of these other logos. Some of you, these may be familiar to some of you. But you got some heavy hitters here. And what this guy just said is that that this company has the largest database of brain waves for healthy individuals that are able to do things like pick up a bottle of water. Now, just the fact that they have this stuff to me is of note. Whether or not I'm concerned, that's for each of you to decide. But the fact is they have this. How did they get this? What is the quantity of neural patterns that they actually have? Where do they get this from?
But also what happens to a patient following a stroke that can no longer hold this glass of water? What are the anomalies in the radio stations? And with that in mind, I'd like to talk a bit about BQ 1.0, our device. So as you can see here, this is a patient sitting in the chair. Every single treatment is asked to do certain motor tasks, like grabbing this glass of water. And we are collecting his EEG data and motor data, running it to the cloud, running machine learning algorithms, and retrieving back a tailored electromagnetic treatment.
A tailored electromagnetic treatment. So they read your brain in a laboratory environment. This is just what they're sharing. Read your brain. No contact, right? They're using antennas and they're using coils. Reading your brain, putting it through the cloud, using machine learning and algorithms to then tailor a unique electromagnetic therapeutic for you.
It's important to say that this device is unique in several aspects. First, it's probably one of the first in the world which is a therapeutic machine learning-based device, also a therapeutic cloud-connected device. It's non-invasive, it's patient-friendly, and it's about an hour treatment a day. And we are very fortunate to have IBM sharing with us this vision of digital therapeutics.
Digital therapeutics using antennas.
Right now, the company is in clinical trials in several leading hospitals in Israel and abroad, and I cannot share much at this point, but I do want to give you a flavor of where this is going. What you see on the left-hand side are paralyzed rats following spinal cord injury. And you see that the starting point is, well, the rat was paralyzed, and the spine itself is almost completely cut. And over the course of 2 months treatment, what we've seen is a 0 to 1 effect. Paralyzed rats started to walk again, and you can see the MRI DTI talks for itself, a connectivity in the spine. But I do want to share with you today also some of our results already in human.
So this totally, basically, completely severed spine in a mammal. In this case, it's a rat, what they're sharing with you. And he disclosed that there's a lot going on that he can't share with you. And after a 2-month period of time, a mammal with a basically severed spinal cord was able to walk again. And what they show you there in fluorescence is this regrowth of nerves and this retraining of the neural circuits, which if you go to humaninternet.org and you look under bioenergy and you go to BrainQ, you will see the patents that are associated with this company, and they talk about using things like coils and antennas to treat nervous systems after trauma, stroke, or a spinal cord injury. Just one example. They also have enhancing your brain activity, which does the same kind of thing in your brain. They can regrow damaged areas of the brain, just like they can regrow damaged areas of the nervous system. And they can resonate specific neural circuits. They can turn them off, turn them on, enhance them, and basically cure things like paralysis. And we'll continue.
This result has been just recently published in the World Congress of Neurorehabilitation. What you see here is a guy, a 32-year-old guy, following a very severe accident where he lost all motor and sensor below a certain part of his body. And over the course of 4 months treatment, he regained sensation back to his legs. And look at the MRI results. It talks for itself. And moreover, it somewhat replicates what you've seen on the left-hand side. And I just want to give it to you as a taste that we believe that we are into something very fundamental here.
This guy's talking about using electromagnetic fields to do things like reattach a spinal cord and have it work again. I just want you to try to get your mind wrapped around where the hell we're going here. And how many electromagnetic fields are you around right now? Open up your Wi-Fi and see how many Wi-Fi access points are nearby. And then think about how many devices you have in your house and maybe how many devices are around in your neighbor's house. Because if you can see all of those Wi-Fi access points, chances are any of the devices that are attached to those Wi-Fi access points also are emitting energy that you are in contact with. Just saying. And this guy's talking about electromagnetic fields being able to do things like reattach, reassemble, reconfigure a freaking spinal cord.
We are very much out of time, and I need to keep it on 4 minutes, apparently. So I will just say that we sit in Jerusalem. We are a 12-people company, well-funded, and we are with, I think, some of the most brilliant people in terms of AI and neuroscience. Really all joined on this mission of bringing cure to millions of people around the world. We welcome you to join us or approach us and find a way to collaborate. Thank you.
Let's see how long this one is. Because this is Google.
My name is Yotam Drexler. I'm the CEO of BrainQ.
BrainQ is developing an AI-based medical device aimed at getting paralyzed people following neuro disorders like stroke or spinal cord injury back on their feet. Every single year, hundreds of millions of people around the world suffer from neuro disorders. Stroke alone accounts for 15 million people every single year, and the entire neuro disorders cost to the US economy is $1.5 trillion every single year. My grandfather had a stroke several years ago. From being the center of the family, all of a sudden he became paralyzed in half of his body. That means he can no longer do simple things like grabbing a glass of water or dressing alone. And that's the reality for many people out there. The common treatment is what's called physical therapy. It's essentially exercising the hand or the leg back and forth. What BrainQ essentially does is modeling physical therapy and applying it directly to the brain. In a sense, we ask what happens for a patient or for a healthy person when he does an hand movement, like, reaching his hand to grab a glass of water. So we get a lot of people do this kind of movements, and then we learn the patterns. We take these patterns that we have learned and identified and reapply it back to him as a personalized treatment. We have developed a unique brain-computer interface-based medical device. It takes patients' brainwaves as an input with a set of metadata and runs machine learning algorithms in the cloud and translate them into a tailored electromagnetic treatment aimed at facilitating their central nerve system recovery process. And we were very fortunate to have Google share this vision with us. We worked very closely with the GCP team on making this vision come true. We were fortunate to be on this program, and it really puts us on a fast track. In all four fronts, we have developed the next generation of technology with precision medicine base, with the studio team, Peter Norwick, and the rest of the Googlers that were very, very keen in helping us. We had a large funding round in the past couple of months, and we had several collaborations in the pipeline, and we are hoping to continue on this promising track and really bring cure to millions of people around the world. And we are fortunate to have Google with us on this journey.
Yeah, so Google loves you. Good night.